It's the AEMT lecture series. Welcome back. This will be video number 2 for Chapter 8. So welcome everybody. Hope everybody got something out of the previous video. And so we will continue our journey with Chapter 8. Let me get a little bit organized real quick here. I think I'm ready to begin. All right, so we're going to talk a little more about acid base. Not too much more. We're going to reinforce what you already know, right? So that's the plan here. All right, so hang on one second. All right, so we know that CO2, carbon dioxide, right? It's going to mix with some H2O, which is water. And we're going to get that H2CO3, otherwise known as carbonic acid. Okay. Carbonic acid is a buffer, okay? Because it can go either way. If something's too alkalotic, meaning the pH is really high, we can get some acid going to bring the pH down. Right, and then if the pH is too low, we could get some bicarbonate, which is right here, HCO3, and that'll make it less acidic. And it's all about being a hydrogen ion acceptor. Okay, so you'll see here that we have 2 hydrogen here, and we only have 1 here. So it allows us to rid ourselves of that extra hydrogen and make it less acidic. Excuse me. All right, so let's so that is our equation. That's how it works. And so again, carbonic acid, weak acid, holds on to the hydrogen ion, right? CO2 coming from the respiratory system. Remember, we mentioned that there's actually 3 buffer systems, right? 1 right here at the intracellular level, 2 your respiratory system, and 3 your renal system. So CO2 is not as quick to react to increases or decreases in the pH level, but it's the next quickest thing because it responds within minutes. And we already talked about this being your chemical buffer system, right? You have your H2CO3, which is your carbonic acid, and then your bicarbonate, and losing a hydrogen ion is the difference, and it's a big difference, all right? We go from acidic to being non-acidic. And then we talk about the renal system, right? So the renal system could take many hours to days before it will respond to increases in pH or decreases in pH. However, the renal system can do a couple things. 1, it can get rid of waste faster by, letting urine go, larger quantities and going more often. But it also has the ability to hold on to bicarbonate, which would, help you out if you're real acidic, to save as much bicarbonate as possible. All right. And then here again is our 3 buffer systems, right? And so we have the immediate, and the immediate here is at the intracellular level, all right? So, of the bicarbonate or carbonic acid, the buffer system. Within minutes, again, is your respiratory system. Hours to days with the renal system. All right. breaking it down for you. All right, so you can write it as many ways as you want to, right? But CO2 plus H2O gives us H2CO3, right? That's that carbonic acid. And H2CO3 but breaks down. See the 2 hydrogen here? You notice only 1 hydrogen here. We went from 2 to 1, right? So we can lose that hydrogen if we are too acidic to make bicarb, and that free hydrogen hangs out there. All right, let's talk about the normal values. All right, so on a normal day, we have CO2 plus water will give us that carbonic acid, and then depending from minute to minute, whether we'll need to control pH with our bicarb, and then your free hydrogen ion, right? That right there, I'm sorry, right, is just a representative of us losing a hydrogen or gaining hydrogen. All right, and then you'll notice right here is the first time that we've, in our course, that we've shown an EtCO2 reading, right? So this will become important in the field now that you know about acid base, and you know increases in CO2 produce acid, right? No, it's not good. We can look at end-tidal CO2 and kind of get an idea where the patient's at. So increases in CO2 are indications that the patient's retaining CO2 and we have a threat of becoming acidotic. All right, 35 to 45 is a normal reading, somewhere in that range. And so welcome. And I know Instructor Lillard is very passionate about end-tidal CO2 readings, and quite he should be. It is well, becoming known as the 5th vital sign. So very, very important. He was preaching it when it wasn't cool, though. So, yeah, respiratory sources, metabolic sources. All right, so yeah, there's your PCO2. That's what this represents right here, 35 to 45. Right, can't be measured. Can be measured in the field by capnography, and that's end-tidal CO2 is the reading of capnography. The pH, right? So this is a normal pH for us. Remember, we're doing pH of blood. 7 is considered basic, and so blood usually runs between 7.35 and 7.45. All right, let's look at somebody, possibly not breathing. What do we have here? We have CO2 plus water has given us the carbonic acid. And then the problem is that the bicarb will soon not be enough to overcome the acidic state, because you're going to have, see this hydrogen ion right here? It's going to be increasing, right? So it would, hang on one second, let me get my pen up here. Remember I said it's all about the H. And so the hydrogen ion in this case will be increasing. The patient will be becoming more acidic. Right. Oh, I like the sound effects. All right, so we talk about driving the reaction to the right. Remember, that's how this works, right? CO2 plus water gives us this. If we have carbonic acid here, that's going to continue to drive it to the right and allow bicarb to come into the game. Oh, see, they were thinking with me, increasing that. Decrease in pH, so I didn't tell you, we should have talked about that. So we talked about on the last slide, we said normal pH is 7.35 to 7.45. So you know enough now about pH to whether you should be able to kind of give me an indicator. Is this pH level going to go up or down? I'll give you a second to call me and answer. No, I'm just kidding. All right, so yeah, the pH in this instance we're becoming more acidic, it will be going down. So pH will be going down, right? So we have a decrease in pH. We have an increase in CO2, right? And that, my friends, is called acidosis. All right. Congratulations. It's really not that hard, is it? So an acute I can say that because I've been teaching this stuff forever. Not even really forever, but I've been teaching it for a little while. And, so I got it. But I know if you're still struggling with it, I'm not trying to say, oh, it's so easy. Because it's not always so easy. All right, so an acute condition, only first acid-base stabilizer bicarbonate buffer immediately, right? So when we're talking about respiratory acidosis, and that's what we're going to get into in a minute in the slide program, but it's acidosis related to a respiratory problem, right? So if we're retaining CO2, from a respiratory problem, we consider that respiratory acidosis. And again, an acute condition. So we need bicarb to kick in, but will bicarb be enough? All right, so let's talk about it. Pre-hospital care, right? That's what we need. And I've talked about it. I know you hate hearing it, but there's a cost, right, for everything, right? And that cost in this case is going to depend on how sick this patient is, right? So is this somebody that's asthmatic and they're in moderate to severe distress, and you're considering doing albuterol atrovent treatment? Is this somebody that we'll just start it when we get to the truck? Or is this something that we want to start right away? Asthmatics will decompensate quickly, especially adult asthmatics, because they've already waited quite some time before they've activated 911, because they've become comfortable over the years of dealing with asthma. So they've become comfortable in understanding what it feels like to not be able to breathe, and they don't panic. That's why sometimes when you're working in an asthmatic cardiac arrest, that they occur. A lot of times the patient just put it off until it was too late, right? And so the way to fix this, right? So if at the cellular level, if we are given as much bicarb as we can, that won't be enough, will it? So we mentioned the respiratory system is within minutes, right? So what can we do? All right, so we know that in mechanical ventilation, the more the patient gets rid of CO2, the better, right? So we need to provide whatever treatment's necessary to introduce oxygen coming in and allow that CO2 to escape, right? Now, so this was a theory back in the day, when I was in EMT and paramedic school, we hyperventilated everybody, because it's probably what you're thinking right now, maybe. Probably think, well, if that's the case, why don't we give 100 breaths per minute? Well, because we found out that we can actually increase that intracardiac pressure, right? And we can actually cause problems circulating blood through the system. And that's even as bad sometimes, because we're not delivering oxygen to the cells, which is hypoxia, the definition, right? So we just got to be careful how we ventilate. But if we can just start getting CO2 out and O2 in, that's the easy fix in this case. Open CO2, get rid of it. That way we can drive the reaction back to the left, right? We can start getting bicarb, moving this back in, going from right to left, or in this case, left to right. Ventilate. Ventilate, ventilate, ventilate. Let me get rid of this ink. Stand by so you can see the slide. All right, drives reaction back to the left. Decreases that oxygen. Not oxygen, but definitely decreases that free hydrogen though, right? Right there. So that's what we want to do. We want to drive that hydrogen level down, because what is hydrogen? It's acid. In our case, that's all we need to think about. If we see an H and it's got a plus by it, that means there's more than one. We got to get rid of it. So it actually means it's positively charged. But anyway, there's more than one in this case. We need to get to drive that down. All right. Results in return of pH with hopefully normal limits, right? So if we are, let's say we're at 7.21. No, that's not indicative. Let's say we're at 6.0, right? Because 7.35 to 7.45 is normal. If we're at 6.0, that's telling you what? If we're at 6, we're less than 7, that means we're acidic, okay? So hopefully we can drive that pH up in this case back into the 7s. That's where we want to be. And driving the hydrogen ion down, reducing that hydrogen ion and bringing the pH up back to normal. All right, so back to our normal slideshow here. The pH, right? It's a measure of the acidity or alkalinity of a solution. We just talked about that. Lower values represent acidic, higher values represent alkalosis. And so, yeah, you can have just disturbances of your acid base system, and it can be associated with disturbances in potassium as well. Okay, I'm just checking my notes to see if I'm missing anything. All right, I'm not. That's good. Let's keep going. So let's talk about